air conditioning unit with a circuit ampacity of 48.5 amps is protected by a 30 amp breaker, but the unit is pulling 41 amps without tripping the breaker. The circuit ampacity signifies the maximum safe current the circuit can handle. The breaker should trip when the current exceeds its rating. The fact that the 41 amp draw isn't tripping the 30 amp breaker indicates a problem. The breaker might be a thermal magnetic type, which incorporates a time delay feature. This delay prevents immediate tripping from brief current surges, allowing the circuit to handle temporary overloads. However, a sustained overload should eventually trip the breaker as the thermal element heats up. It's possible the overload hasn't lasted long enough, or isn't severe enough, to trigger the thermal element. Besides the breaker issue, other factors in the electrical system could be at play. Firstly, loose connections in the circuit can elevate resistance and induce voltage drop. This voltage drop subsequently diminishes the current reaching the breaker, potentially hindering its ability to trip. Secondly, undersized wiring poses another concern. If the wiring is inadequate for the load, it can overheat, increasing resistance and similarly impacting the breaker's tripping threshold. Thirdly, a ground fault could be present. A ground fault can bypass the breaker, allowing excess current to flow without initiating a trip. Based on these observations, several recommendations can be made. Replace the 30 amp breaker with a higher amperage breaker, selecting either a 45 amp or 50 amp breaker, depending on the specific circuit ampacity requirements. Thoroughly tighten all connections within the circuit. This includes connections at the breaker itself, the air conditioning unit, and any other devices incorporated in the circuit. Conduct a comprehensive inspection of the wiring to identify any signs of damage or instances of undersized wiring. If a ground fault is suspected, it is crucial to engage a licensed electrician for a more in-depth investigation and any necessary repairs. Breakers are designed with specific trip curves that dictate how they respond to overcurrents over time. A breaker's trip curve illustrates the relationship between the magnitude of the overcurrent and the time it takes for the breaker to trip. These curves are standardized and categorized by types like Type B, Type C, and Type D, each exhibiting different tripping characteristics. A Type B breaker, for example, trips relatively quickly under moderate overcurrent conditions, while a Type D breaker tolerates higher inrush currents for a longer duration. Understanding the breaker's trip curve is crucial in determining whether it is functioning correctly. To assess the breaker's functionality, you can employ a breaker tester. A breaker tester applies controlled amounts of current to the breaker and measures the time it takes for it to trip. By comparing the tripping time with the breaker's published trip curve, you can ascertain whether the breaker is operating within its specified parameters. If the breaker consistently fails to trip within the expected time frame, it may be faulty and require replacement. Another factor to consider is the ambient temperature surrounding the breaker. Breakers are calibrated to operate at a specific temperature, typically 25 degrees Celsius or 77 degrees Fahrenheit. If the ambient temperature is significantly higher or lower than the calibration temperature, the breaker's tripping characteristics can be affected. High temperatures can cause the breaker to trip at lower current levels, while low temperatures can delay tripping. To mitigate the effects of ambient temperature, it is essential to ensure that the electrical panel is adequately ventilated and that the breakers are not exposed to direct sunlight or other sources of heat. Furthermore, it's essential to consider the conductor ampacity, which is the maximum current a conductor can carry continuously without exceeding its temperature rating. The conductor ampacity is determined by factors such as the conductor material, size, insulation type, and installation method. The National Electrical Code, or NEC, provides tables that list the ampacities of various conductors under different conditions. For instance, NEC Table 310.15b16 outlines the ampacities of insulated conductors rated up to 2000 volts based on an ambient temperature of 30 degrees Celsius or 86 degrees Fahrenheit. It is crucial to select conductors with an ampacity that is equal to or greater than the circuit's calculated load current. In this scenario, the #10Y may be undersized for the 48.5 amp circuit ampacity, potentially leading to overheating and insulation damage. If the #10 wire is rated for 30 amps, it is insufficient for the load. The conductor size must be upgraded to match the circuit ampacity requirement. Voltage drop is another critical factor in electrical circuits. Voltage drop is the reduction in voltage that occurs along a conductor due to its resistance. Excessive voltage drop can cause equipment to malfunction, reduce lighting brightness, and increase energy consumption. The NEC recommends limiting voltage drop to a maximum of 3% for branch circuits and 5% for feeders. Voltage drop can be calculated using Ohm's law and the conductor's resistance per unit length. To minimize voltage drop, you can increase the conductor size, reduce the circuit length, or use conductors with lower resistance. In this case, the long run of #10 wire may be contributing to excessive voltage drop, further hindering the breaker's ability to trip and potentially damaging the air conditioning unit. The type of load also influences the breaker selection. Air conditioning units are considered inductive loads, meaning they draw high inrush current when they start up. This inrush current can be several times higher than the unit's running current. To accommodate the inrush current, it is crucial to use a breaker that is specifically designed for inductive loads such as a hacker, heating, air conditioning, and refrigeration type breaker. Hacker breakers are designed with a time delay that allows them to withstand the inrush current without tripping. Using a standard breaker for an inductive load can result in nuisance tripping, where the breaker trips unnecessarily during startup. In addition to the breaker and wiring, the air conditioning unit itself could be contributing to the problem. A malfunctioning compressor or other internal components can cause the unit to draw excessive current. To diagnose this, you can use a clamp meter to measure the current draw of each component in the unit. If any component is drawing excessive current, it may need to be repaired or replaced. Furthermore, ensure the air conditioning unit is properly maintained. Dirty air filters, clogged coils, or low refrigerant levels can cause the unit to work harder and draw more current. Regularly cleaning the air filters and coils and ensuring the refrigerant level is correct can help to reduce the unit's current draw and prevent overloading the circuit. It is also important to verify the voltage at the air conditioning unit. Low voltage can cause the unit to draw more current in an attempt to maintain its output. Use a voltmeter to measure the voltage at the unit while it is running. If the voltage is below the recommended range, you may need to investigate the electrical service to the building. Loose connections at the service panel, a faulty transformer, or undersized service conductors can all contribute to low voltage. In addition to the electrical aspects, consider the overall efficiency of the air conditioning unit. An old, inefficient unit will draw more current than a newer, energy-efficient model. If the unit is nearing the end of its lifespan, it may be more cost-effective to replace it with a newer, more efficient model. This will not only reduce the unit's current draw but also lower your energy bills. When replacing the breaker, it's vital to adhere to the NEC guidelines for breaker selection and installation. The NEC specifies the types of breakers that are permitted for different applications, as well as the proper methods for installing and wiring breakers. Ensure that the replacement breaker is UL listed and has the appropriate interrupting rating for the circuit. The interrupting rating is the maximum fault current that the breaker can safely interrupt. It is also essential to properly torque the breaker connections to ensure a secure and reliable connection. Using a torque wrench to tighten the connections to the manufacturer's specified torque value will help to prevent loose connections and overheating. A proper grounding system is crucial for electrical safety. The grounding system provides a low impedance path for fault current to flow back to the source, allowing the breaker to trip quickly and prevent electrical shock. Verify that the air conditioning unit is properly grounded and that the grounding conductor is connected to the building's grounding system. Inspect the grounding connections for corrosion or damage and repair or replace them as needed. If the building has a ground rod, ensure that it is properly installed and that it is connected to the grounding system. In some cases, it may be necessary to install additional ground rods to improve the grounding system's effectiveness. Surge protection is another important consideration, especially for sensitive electronic equipment like air conditioning units. Power surges can damage the unit's components and shorten its lifespan. Install a surge protector at the service panel to protect the entire electrical system from surges. You can also install surge protectors at individual outlets to provide additional protection for sensitive equipment. When selecting a surge protector, choose one with a high surge current rating and a low clamping voltage. The surge current rating indicates the maximum amount of current that the surge protector can withstand, while the clamping voltage indicates the voltage level at which the surge protector will start to divert the surge current. Arc fault circuit interrupters, or size, are designed to protect against arc faults, which are dangerous electrical faults that can cause fires. A size detects arc faults by monitoring the current waveform in the circuit. If an arc fault is detected, the SI will trip the circuit and prevent a fire. The NEC requires a size in many areas of the home, including bedrooms, living rooms, and dining rooms. Consider installing a size in the circuit that serves the air conditioning unit to provide additional protection against arc faults. Ground fault circuit interrupters, or GFCIs, are designed to protect against ground faults, which can cause electrical shock. GFCIs detect ground faults by monitoring the current balance between the hot and neutral conductors. If a ground fault is detected, the GFCI will trip the circuit and prevent electrical shock. The NEC requires GFCIs in wet locations, such as bathrooms, kitchens, and outdoor areas. If the air conditioning unit is located in a wet location, it should be protected by a GFCI. Electrical panels should be inspected regularly to ensure they are in good condition and free from hazards. Look for signs of corrosion, damage, or overheating. Ensure that all the breakers are properly labeled and that the panel cover is securely fastened. If you notice any problems with the electrical panel, contact a qualified electrician for repair. Finally, safety is paramount when working with electricity. Always turn off the power to the circuit before working on it. Use insulated tools and wear appropriate personal protective equipment, such as gloves and safety glasses. If you are not comfortable working with electricity, contact a qualified electrician for assistance. Improperly performed electrical work can be dangerous and can lead to electrical shock, fire, or other hazards.